So in this video we're going to go over resting membrane potential and action potentials. So some key numbers that you probably should know is that inside the cell it's approximately 65 to 75 millivolts. And that's at rest. And if we were to look at a membrane, for instance, that's inside a cell, what we're going to see is inside, this is the intracell and this is the extracell. And what we're going to see is, in terms of how the nerve is going to behave, or the charge is going to behave across this membrane, we're going to see negative charge kind of on the inside and then positive on the outside. And what's interesting is that this negative and positive isn't really negative positive. It's more like that's the behavior that we see inside and outside the cell relative to the ions that are present. So it's going to act as though the intracellular is lined with negative charge and positive on the outside. And this allows for it to be polarized. So it's that allowing for that charge balance, so that when you need the cell to fire an action potential, it can, because there's this difference in electrical charge. So some terms to know: you have hyperpolarized, and if you think about what it means to be hyper always means more. So in the case of a membrane, it's going to be more negative than the resting membrane potential. So for example, that's going to be like negative 85 millivolts. Now if we're going to say depolarize, we know that the word D means not. So if we think about in terms of polarized, it's going to be not as polarized. It's going to be less negative. And in terms of than the resting membrane potential, and in terms of a charge, if we look at it, it's going to be closer to negative 50 millivolts. And depending on the charge type, or the membrane type, we have the charge ranging from for nerves negative 70 millivolts, for everything else approximately negative 90 millivolts. And so if you think about where this is at negative 70 millivolts, being not as charged, it's going to be around negative 50. Being hyper or more charged, being more negative, it's going to be more around negative 85 millivolts. So just keeping those roots in your memory bank, it makes it a little easier to remember. So now if we look at the actual extracellular and intracellular fluids themselves, so what we have here is a membrane. So we've got our cell membrane right here. And on the left side, this is the intracellular, and on the right side is the extracellular. And we also have a capillary wall. And here's the plasma membrane, or the plasma itself. So if we were to look at what's inside of each of these, what we're going to find is there's some interstitial fluid in the extracellular. And the big thing is we're going to look at the sodium concentration versus the potassium concentration. And that's going to be the same on the intracellular versus the extracellular. And what we're going to find is on the intracellular, we're going to have more potassium and less sodium. On the extracellular, it's going to be the exact opposite. We're going to have more sodium and less potassium. The other thing that's going to be found in the intracellular is organic phosphates plus proteins. And so this asymmetry that we see between the concentrations of sodium and potassium, it's a result of the sodium-potassium ATPase. So it's the sodium-potassium ATPase that is going to kind of act like a pump, allowing for the concentration change of the sodium and potassium ions. And just know that it's the potassium ions that are actually moving back and forth, and they're acting as carriers to allow for this concentration difference. And this is what's going to alter the resting membrane potential so that we can see that charge difference that occurs. Now, in terms of the equilibrium, or the what's considered the norm for what the millivolt range should be for the cell, just know at negative 37 degrees Celsius, we should expect that the equilibrium constant for potassium is negative 90 millivolts. For sodium, it's going to be positive 60 millivolts, and for chloride ions, it's going to be a negative 70 millivolts. And we're going to get into why these numbers are important. And another thing to remember is that the resting membrane potential is going to be equal to the equilibrium constant for potassium. So we expect it's going to be about negative 90 millivolts. And as we said before, if we want the depolarization to occur, so we have an action potential, we're going to have that negative become less. So there are two equations that it's one of those, I wouldn't say committed to memory, it's more understanding of how they came up with these numbers. The first, you've probably seen it and it's basically a variation of the Nernst equation. So it's looking at the ideal gas constant times the temperature divided by the ion valence, or the amount of ions available, times Faraday's constant, times the natural log of potassium initial versus potassium final. And so this formula, of course, the potassium ions versus the sodium ions versus the chloride ions, that's really what's changing here to give you the different equilibrium values. And so just remember, this is one of those things that it's going to help you understand if these numbers were to change, how do they change in relationship to the value you're going to get for the amount of millivolts. Another equation that comes up is the Goldman equation. And this is basically an equation that helps you understand how they calculated the resting membrane potential. And the way this equation works is it's going to be an extension of the Nernst equation, in the sense that we have our ideal gas constant times temperature over Faraday's constant. And now the difference is we're going to look at the values of potassium, sodium, as well as chloride. The significant difference to note here is the chloride ions themselves. We're looking at the initials here, but in the last one it changes. And it's all going to be divided by the exact opposite. So we have, again, potassium, sodium, and now when we're looking at the chloride ions, we're using the final value. And so this Goldman equation allows us to calculate what the resting membrane potential is looking at the different ions themselves. So it's a very important equation and allows us to really understand what's going on. And so the video is not too long. I wanted to let you know the next video is going to be on what exactly depolarization is, hyperpolarization, looking at the sodium versus the potassium channels and how they work. If you want my notes, there's a link below. If you like the video, give it a thumbs up, and please subscribe to the channel. If you have any questions, comments, leave them below.